Good morning, ladies and gentlemen. Let's start off with this today. Draw a circuit using the correct symbols for a battery, bulb, ammeter, and voltmeter.
Do this in your notes. You should be really good at this by now.
Yeah, you probably already have it drawn, okay? So go ahead and draw that. I'll go ahead and draw it over here too. Okay, battery. And then we got a bulb. And we got an ammeter. And we got a bulb. Let me use my colors here. I've got a system in place. Okay, so voltmeter. And then here's my ammeter right there. Okay.
Got to connect them.
Got to connect the bad boys. The ammeter goes in the flow. Voltmeter goes across the L that we want to measure, which I assume is our light bulb.
Yeah. Potential difference. The difference in electrical potential energy from one side of something to the other.
Okay. If you still need it, positive and negative side of the battery. Okay. Okay, so if the current is 0.145 amperes, 0.145 amperes, and the delta V is 1.5 volts, so the potential difference is 1.5 volts. What is the resistance of the bulb? Okay, so it wants to know the resistance of the bulb.
That's Ohm's law.
Ohm's law! Okay, so we want to know the resistance. Resistance was volts over current, right?
Yeah.
Okay, so we have our voltage right here, which is 1.5.
So go ahead and calculate that your own
Oh,
bad
yeah, don't
self.
look at me yet. Sorry, I'm looking at myself. Okay.
And we're back.
Pause it. Yeah, make sure you pause it. Okay, and then the current is 0.145 amperes. And I plug it into my handy dandy calculator.
Not so handy if it's over here.
All the way across the room. Okay, thank you, sir. Okay, we got 1.5 divided by 0.145, and I get 10.3 ohms. Okay, so 10.3. What was the symbol for the ohm again?
That was that Greek letter omega that looks like Mary Tyler Moore's hair.
Yeah, it's the haircut, right? Okay. Okay, so that was the resistance, right? What is the power output of the bulb?
Power is, what's that equation for
The
power?
output of the bulb. Okay, so power was intravenous. IV, that's an I. Okay, so I like that. Okay, so our current is 0.145 amperes times our voltage across that bulb is still 1.5, right?
Yeah.
Okay, so power equals, let's do it. 0.145 times 1.5, and I get 0.22
What?
watts. 0.22 watt. What? Okay. So
Simple,
don't forget,
yes.
Yeah, so don't forget, power is brightness, how bright something is, right?
Yep.
So we can compare brightnesses by looking at the different powers that we have. And pay attention to the two players that are involved with power.
Absolutely.
This more also doesn't have her mouse ready. Go. Okay, see it on there? There it is. Okay, power. It went on the first click. See that?
Oh.
Okay, so power is the rate that energy is changed from one form to another.
Okay, well, now, what kind of power, what kind of energy changes are going on in the light bulb?
What kind of energy change is going on in there? What do you mean by that, Boykin?
Well, you've got electrical energy.
Oh, and it's being changed when we see the light. Is that what you mean?
Yep. Mm-hmm.
When we see the light in a light bulb, what kind of energy change is going on there? We've got electrons, electrical energy running through the wires, right?
Yeah.
And when it gets to the light bulb, we see light,
Yep.
right? So it's being changed into light energy.
Yep.
And what else?
Well, those bulbs get hot.
Yeah, so heat, right?
So heat and light. But where is that energy for the circuit coming from?
Well, it's coming from
The battery.
battery, right?
So where does the electrical energy come from?
So the electrical energy comes from the battery.
And what form of energy is in the battery?
Well, we have a chemical reaction there
Yep.
that produces that reaction, that energy, right?
Yeah, the chemical. So you've got chemical energy into electrical energy in the
There
battery.
we go. That's what I'm trying to say.
And then you've got electrical energy into heat and light in the bulb.
It's a whole process. Okay, So here is our equation for power. We just said that power is the rate that energy is changed from one form to another. So a rate, just like velocity, meters per second.
It's got time on the bottom.
Time on the bottom, and then energy at the top. The rate of change that energy, the rate of time that energy changes. Okay, a rate.
Yeah.
We also know that power is current times the change in electrical potential difference there.
You know, it occurs to me now that I look at this, we probably should have the units for current and the units for volts. What is it? What is an ampere and what is a volt?
So an ampere is so for current, an ampere is how many joules per second. Coulombs per second. Because we're talking about the electrons, right?
That's right.
Coulomb per second. And then our delta V.
Electrical potential difference.
Okay, our delta V, that was work over charge, right? So joules per Coulomb, right? I was going to put a Q there. Per Coulomb, okay?
So we've got...
Should I put this up here?
Yeah, I like that. I times V, you got coulombs per second times joules per coulomb.
Okay, so what happens here? These cancel out.
You got joules per second.
Joules per second. Okay?
Which is a what?
Which is what? Which is joules per second, right there. Okay. Oh, wait, we actually had that over there.
The old man didn't
we
notice
got too excited, okay? But I like it better. I like how we explained it.
Well, I also noticed how this line has moved.
Yeah.
Oh,
you don't want to know why? It's because I moved it up a little bit to put this in there. Yeah, these two lines should be going through the two C's right here.
Yeah.
Okay. All right, so hopefully that makes sense. Bada boom. Oh, go back. I apologize. Okay. Take a minute. Go ahead and pause the video. You're gonna go to page 511, and you guys are gonna do numbers 1 through 3. Just a little review here. 1, 2, and 3 right here.
They're real simple, and the idea is you do them a few times, and then you got it. Okay. So pause this, and we'll be back.
So do you think we should do it with them right now, or should I just go over it with them for homework the next day?
That sounds like class stuff.
Class stuff, okay. All right, so we will go over those tomorrow. I'll put that in the note in the homework description as well. But you should pause them and do them right now to see how you're doing.
Yep.
Okay. All right, so rocking and rolling. In a circuit, current passes through a series of parts.
Yep.
Right?
Yep.
All right. As charge flows through a part, its energy either goes up or down.
That's an important thing, yeah.
Yeah, it either increases or decreases, up or down, up and down. Okay, it's important. What does the battery, the 1.5 volts battery do? Sorry, I was looking at my drawing. What does the 1.5 volt battery do to energy of the 0.145 amperes of charge flowing through it? Okay, well,
you should be able to answer this question.
Yeah, so it increases. So the options are: does the energy go up, increase, or down, decrease? And the battery is going to increase the energy of that electron, right, of that charge.
And it does it by using chemical energy.
Yes. And here we go. What does the bulb do to the energy of the 0.45 ampere charge flowing through it if the potential difference across the bulb is 1.5 volts? Okay, well, we know that there's a change here, right? Yeah. And this bulb is going to be decreasing the energy. The energy is going to go down.
Of the charge flowing through it. And what happened? There's a conservation of energy, can be neither created nor destroyed, only change from one form to another. So we get your heat and light. Okay.
And so hopefully you guys caught Mr. Boykin said, because it's super important, this idea of the conservation of the energy. As we go as the electrons move from here to here, we lose energy, but it doesn't just disappear, right?
Right.
Okay, Mr. Boykin said it gets lost, not lost, it gets changed into two other forms, heat and light. Okay, so that makes sense. Okay, would a higher resistance bulb let more or less current flow through it? Let's start with that question.
Well, what is resistance?
Well, resistance is defined by this equation right here, right?
Yeah.
Okay, so if it had more resistance, it's going to have less current flowing through it.
Yep, for the same voltage, you got 1.5 volts across it. Resistance is how hard it is for current to flow through something. It's like it's easier to run through air than it is to run through water.
Yeah. Okay, so that makes sense, right?
Yeah.
Would it be brighter or dimmer?
So if it's got less current, would it be brighter or dimmer?
Well, let's take a look at our equation right here, right?
Yeah.
Power has to do with brightness, right? If we have less current, and the voltage is the same, what's going to happen to our power? It's going to go,
Be less.
okay? And what does that mean for our brightness? It's going to be dimmer.
Yes,
right?
ma'am.
Not as bright. Did we want to explain a little bit more about that? Or is that,
Well,
because we were talking a little bit about the units.
well, that's true. And it's if you have fewer coulombs flowing through
Coulombs being
and
charged.
fewer coulombs, and you've got 1.5 volts, which is a joule per coulomb. So there's going to be 1.5 volts joule per coulomb, and you have fewer coulombs, you're going to have less electrical potential energy change. There's going to be less energy changed from electrical to heat and light because you got fewer coulombs flowing through.
That makes sense. It's all about the coulombs,
That's
right?
right.
Our electrons, right?
Yep.
Okay, the rate at which they're going through stuff, and how much there is. Okay, so would it be brighter or dimmer? We already did that. Okay, so look at the diagram on page 509. Boop, 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 boop. Okay, and the question is, anything weird here? Huh.
Page 509.
So this is kind of like a circuit, right? That's what they're showing here?
Yeah.
Now, what do they have flowing in the circuit?
Positive charge flow. What the?
What the heck? We have been talking about electrons, Miss Moore. What is going on? And so, why is there positives there? You guys remember Benjamin Franklin?
Yeah.
Good old Benji. So he back
Sign
in
of the
day-
Constitution.
Yeah,
One of
yeah.
the great, and also one of the great scientists of that age.
So he thought that instead of electrons, that there was positive charge carriers
Yeah.
in the wires. And so we've been talking about how current is electrons, right?
Yeah.
And he had it kind of flipped.
Remember, this is in the 1700s when electrical phenomena were first being discovered. And electricity was described as a fluid, something that would flow. And that it would flow from where there was too much electrical fluid to where there was not enough. So he
guesses.
thought that it was positive stuff, too much, flowing to where there was not enough.
Yeah. Oh, and
And so
do they have the? Oh, they don't have. Oh, here. Okay, we'll go to my next slide. That reminds me of how it flows. Okay, so conventional current. This is a new term for you guys.
Yeah.
Conventional current.
and that's symbolized by the capital letter I.
Yeah. So it moves from positive to negative. Now, does this make sense?
Well, it doesn't make sense according to what we've been doing.
Yeah. So the concept of conventional current is it should raise a red flag in you. Does the flow?
Well, if there is a positive charge carrier in the wire next to the positive side, what kind of force would it experience?
Repulsion, right?
Repulsion.
Okay.
And if there was a positive charge carrier in the wire, what would experience near the negative charge?
Attraction.
Negative. Attraction.
Right? But like we said, we know that electrons are what are actually flowing, and we know that electrons flow like this.
Now,
Is that what you're gonna say? Is that okay, Brooklyn?
yes, yeah, that's good.
Is that where we're gonna go?
But now, why is this? Well, it's a model. And physics, there is a culture in anything. There's a culture in any job, in any profession, in any discipline. And in physics, you have these old people, well, I learned it was positive and negative, I conventional current. That's the way I learned it, is that's the way it's going to be. And so you have old people run the world, right? Have you ever noticed? And so I'm old. And so,
You can say that.
however, I do not run the world. If I did, I'd throw out conventional current. We just do electrons. But the idea is it's a carryover from an earlier age, and it's a model. And all models attempt to describe observable phenomenon. And they have good things about them and bad things about them. And really, we know much, much more about electrical phenomenon, and it gets even crazier that we're not even going to talk about it.
Well, and for you guys who are going to go into college, conventional current will be in your college textbook.
Yep. Yeah.
I can't remember. Do they talk about electrons in there?
They do.
They do. So they talk about them both. So what
They
you're
do.
getting now is the same thing you'll get later. So you're just getting.
When you get into circuit analysis, then it's conventional current.
Yeah.
Just because it's always been that way.
Yep. All right. So the types of questions we'll ask you on this is to identify which direction the conventional current is going. So
Yeah.
can you do this?
Yeah.
Can you? And do you understand it? Okay. So on your circuit diagram, please show the direction. Oh, we did this.
Well-
about the electron flow and conventional current.
So you've got a diagram. That was the first thing we did in today's lesson. Go ahead and put the E and show the arrow. Now, I'm not going to show them. They'll have to rewind.
I like it. I like it. Make it work.
We're asking them to do it.
Okay.
In the direct, and remember, it's going to depend on the direction of the battery. Yeah, which side's positive, which side's negative.
Yes. Okay. Moving on here. So I think this is our second to last slide here. Yep. Okay. So make a circuit diagram of the circuit on page 516. I'm gonna erase this for you. You get there.
So page 516, dry cell is another word for a battery. And you know what the symbol for that is. Here's a light bulb and an ammeter and a voltmeter. Now they've got these lines representing the wires, and that's kind of looks like what we have when we've made our circuits. And so convert this picture into a diagram, paying careful attention where the wires go. Okay?
Pay no attention to the man behind the curtain. I shouldn't have erased my thing. It looks like it's the exact same. Okay.
2 amps, 6 volts.
6 volts.
6 volts, 2 amps.
Ah, nice round numbers. Okay.
So, gee, Ms. Moore, that looks exactly like the circuit we drew a minute ago.
I know. I should have kept it up there. I was like, I couldn't remember what the picture looked like. Okay. So make a circuit. We labeled our stuff. And battery polarity. That just
On your diagram, battery polarity, which is positive, which is negative.
Yeah. So what does it want us to do? Calculate the resistance and the power. You know, whenever I hear the word resistance, I always think about Star Wars. The resistance.
Resistance is futile.
Yeah, my sister and my dad, they rewatched all the things over spring break. No life, no.
So is this something that they could do, or should we do it for them?
Oh wait, this is something you guys can do.
Yeah.
Oh yeah. Okay, so we got a lot of stuff for you today. So not that much, but so for homework, I want you guys to calculate the resistance and the power of this of the resistance through the light bulb there, and the power that the light bulb is going to be going to have. Then also show the direction of the electron flow and the conventional current. And then lastly, page 515, numbers 5 through 7, and don't forget numbers 5, 6, and 7, right?
Yep.
And then also earlier we asked you to do numbers 1, 2, and 3 here. So you should already have these done. If you haven't had them done, now you're like, oh no, I've got way more homework.
And we'll talk about them in class.
Okay.